Hey guys, so in this video we're going to be going over Leetcode 128, longest consecutive sequence. So if we just read through the problem description, we're going to be given an unsorted array of integers called nums, and what the algorithm is asking of us is to return the length of the longest consecutive element sequence, and it wants us to write that algorithm in linear time. So if we look at the first example, we have this input array of 104, 200, 1, 3, and 2, and it's telling us that the longest consecutive sequence is 4. The length of the longest consecutive sequence is 4. So the explanation is we have, this sequence exists within here, but if we look at this, we don't exactly get that. So what does this basically mean? It just basically means if you look at the array, return the length of the longest chain of numbers that are directly next to each other in the sense of like counting numbers or integers. So if we look at this, we have 1, then we have 1 plus 1, which is 2. We have 2 plus 1, which is 3. We have 3 plus 1, which is 4. So that's what this array over here represents. So again, if we look through this, we're going to see we have 0, 1, 2, 3, 4, 5, 6, 7, 8, which is of length 9. And the reason that this algorithm is tricky is because these numbers are unsorted. And so how are we figuring out what that length is? Let's try to understand it. Hey, so to try to figure out how to construct the most optimal solution, we're going to start out with this array as an example. And if we just eyeball it, we can see, yes, that it's unsorted, but just by looking at it, we can see that the length of the longest consecutive sequence is 4, right? So if we start at 100 and then go all the way to 103 through the path of 101 and 102, we see that the length of that sequence is 4. And again, remember, the definition of the longest consecutive sequence literally just means integers that are contiguous, meaning if you add 1 or subtract 1 from it, that number also exists in this array. So we know from the Leetcode description of the problem that a solution exists that runs in O of n time. So because we know that, I'm not going to go through and diagram out how the brute force or any other sort of suboptimal solution works. But maybe we can spend 2 seconds talking about it. Basically, I think most people would look at this and see, okay, if I sort the array, then it'll be easier to calculate the length of the longest consecutive sequence. Maybe you use some sort of sliding window approach, or maybe you just have variables that represent counters and you increment them by 1 every time you get a number that is 1 greater than the one before it, and then you compare it to some sort of global counter, and at the end of that you will have the length of the longest consecutive sequence. Now, because we're sorting and then doing a linear scan in that one, we're going to get O of n log n time, which is, maybe if we didn't know that there was a linear time solution, we would think that that is possibly the most optimal one, but because we know, we're just going to hop into it. So with a lot of these array integer problems, there is a pattern that comes up that is that of using a dictionary hash map sort of data structure to track the entries in the array, and then to leverage the constant lookup time of the hash map, and then build our solution up from there. So if that doesn't make sense, let's start working through it, and then we will see the trick to solving this problem. So if we're just going to loop through this linearly, and we're going to start at 1. We're going to say, does 1 exist in this dictionary? No, it doesn't. So we're just going to put 1, and we're going to set it equal to true. We're going to do this for all the numbers. So then we go 100, and I'm using T just to signify true. Then we're going to get 103 true all the way down to 102 2. So I'm just going to do this really quickly. True, then we get 3 to true, and then we get 101, set that equal to true, and then we're going to get 102 and set that equal to true. So now that we have this dictionary that is in a way a replica of this array, but allows us to look things up in constant time, how are we going to figure out what the length of the longest sequence is? Well, there's actually a really cool trick that leverages what we can say is the reality of a sequence. So what we're going to do is we are going to loop through this array, the input array, one more time. And in that loop, what we're going to be doing is seeing what the longest sequence is starting with this number. But that's not exactly true because, well, if we were going to do that, let's say that this first number wasn't a 1, right? Let's say that this first number wasn't a 1 and instead we had a 2 here, and that this was a 1, right? So we swap these two numbers and we start at 2 and we would say, how would we figure out what the longest consecutive sequence is starting at 2? Well, we would look to see, 2 exists in this array, right? And then we would, in this dictionary, we have 2 right here. And then basically we could have some sort of while loop that, would say something like while, the current number plus 1 is in this dictionary, increment some sort of local counter, and then once we reach the end of that, compare that number to a global counter, which we would, call something like max length. And then if that local counter's length is longer than the maximum length, update the maximum length. So if we did this, we would see that at the first, at index 0, the number 2, we would say, okay, we have, at any number, the length of the longest consecutive sequence there is, or the longest sequence is 1. So if we start there, then we would just do a while loop while the dictionary has, the number that is the next one, which would be number 3, increment that length. So we would, starting at 2, we would run that algorithm and we would get a sequence of 2, right? So we would compare that to the global counter, which would initiate at 1. Okay, it's longer than 1, so set it equal to 2. Now, again, to illustrate what I'm trying to do, let's say this wasn't 100 and instead this was 102, and then that this one was 100. So we would do the same algorithm at 102, and we would, go to 102. Again, our local counter is 1. We'd say, does 103 exist? Yes. Then increment it to 103. And then we would say, does 104 exist? No, it doesn't. So then we get something of length 2. Then we get to 103 over here. Running that algorithm would only get length 1. Now, this is the interesting part right here. Let's get to number 1. If we run the same algorithm, we would start at 1, and then we'll check the dictionary. Does 2 exist? Yes, it does. And then we would go to 3. Does 3 exist? Yes. And that would give us a length of 3. Now, if you notice, we've already done the work of looking at 2 and then seeing if the next number exists. And I think you can tell that when we get to 100, we're going to repeat the work we did at 101 and at 102. So there is the possibility of doing a lot of repeated work in here. So how can we get around this? It's a really clever trick, and basically what we're going to do is we're going to iterate through this array from start to finish, and at every number, we are going to check if this number is the start of a consecutive sequence in the dictionary. And only if it is the start of a consecutive sequence, then we are going to use that algorithm, that while loop, to build it out. Now, how do we check if a number is the start? Pretty simple, actually. If we look at the sequence of 1, 2, and 3, over here, if we're starting at 2, how do we know that 2, how do we know just visually whether 2 is the start of this sequence? Well, we know it's not. Why? Because if we look to the left, there's a number there. So how do we describe that programmatically? Well, if the sequence or the dictionary contains the number that is to the left, which means -1, then this number cannot be the beginning of any sequence. So we're just going to move on to the next number. So how does that modify our algorithm? Okay, so we're going to start at number 2 over here, and we're going to say if the dictionary contains the number that is 1 less than this current number, move on to the next number. So using that algorithm, we're going to start at 2. We're going to say, does 2 minus 1, which is 1, exist in the dictionary? Yes, it does. Then continue on to the next number, 102. Does 102 minus 1, which is 101, exist in the dictionary? Yes, it does. So move on to the next one. 103. Does 102 exist in the dictionary? Yes. Now when we get to number 1, we're going to say, does 0 exist in the dictionary? No, it doesn't. So this is the start of a sequence, right? So then we're going to have our while loop, while n plus 1 exists in this dictionary, increment the length of our local counter. And when I use the word local and when I use the word global, local just means it's existing within our loop, and global means it's outside the loop, right? Because when we start at 1, we're going to go to 2, we're going to do our while loop. Does 2 exist? Yes. Does 3 exist? Yes. And we're going to have a count of 3, right? And then we're going to update that and say the longest sequence we've found so far is of length 3. But what happens when we get to this final number, 100, right? So let's go through this. We now get to number 3, and because of our algorithm, we say, does 2 exist? It does. Move on. We go to 101. We say, does 100 exist? Yes, it does. Then move on. Then we go to 100. Does 99 exist? No, it doesn't. So this has to be the start of a sequence. So then we build this up using our while loop and local counter. We go to 100, start at length 1, 101, 101. In here, length 2, 102, length 3, and then we go to 103. Length 4, and we're going to say, how does this length that we've just computed in this while loop compare to the longest length we've found so far? Well, the last one was of length 3, and this one is of length 4, so we're going to update that, and that'll give us the length of the longest consecutive sequence, which is, in the case of this array, 4. So why does this why does this algorithm run in O of n time? So in order to build up this dictionary, we just had to do one loop through this array, and then to calculate the longest sequence length, it took one more loop through this array. So that is O of 2n, right? But as you probably know, we dropped the constant, so that gives us just O of n. And then how much space are we using? Well, we're building a dictionary that is directly proportional in size to the size of the input array, so we get O of n space as well. So that's time, and then that's space. And if this didn't make sense up to this point, it'll make a lot more sense once we go to the code walkthrough. So with that, I'll see you guys in the code walkthrough. Okay, so we're going to start coding this out. We have this method called longest consecutive, and we're taking in that array argument called nums. So the first thing we're going to do is we're going to create a dictionary that is going to track our values. We're just going to use a JavaScript object literal, but you can use a map or a set too. Then what we're going to do is a simple for of loops. We do for const num of nums, and we are just going to check if the dictionary does not contain num. We're going to do dict at num equal true. So this step populates our dictionary with all of the numbers that exist in our array. And now what we're going to do is we're going to create a variable called max length, and we're going to initialize it to 0. The reason we're doing 0 and not 1, you might be wondering, is because if we get an empty array, which is one of the edge cases for this algorithm, we want to return 0. So at the end of this algorithm, we're going to be returning max length. And I do recommend in general when you're doing algorithm problems, whether it's just for practice or even on an interview, it is helpful to think early on, what am I actually going to be returning here? And I try to write my return statement before I code everything out when it's possible, just to have that clearly indicated for myself. So now the meat and bones of the algorithm, we're going to do another for of loop, and we'll do the same thing for const num of nums. We're going to do this, and in here we're going to have a condition that checks, is this number the first number in a potential sequence? So we're going to say if the dictionary contains num minus 1, continue. So remember, we only want to run this algorithm if the number we currently have is the first number in a potential sequence that might be the longest. So now what we're going to do is we're going to create two variables. One variable we're going to call local length. We're going to initiate that to 1, and we're going to have another one that we're just going to call I, which represents the distance from the first number of the current number in our sequence. And if that doesn't make sense, it will in a sec. So that's going to start at 1 also. And we're going to have a while loop that says while dictionary has num plus I. What we're going to do is we're going to say local length plus plus, and we're going to say I plus plus. So what's happening here is, let's say we start at, we have in our dictionary the numbers 1, 2, and 3, and this number right here is 1. We're going to say while num plus I exists. So in this case, it would start at 2, and then it would increment the length of this to 2, increment this to 2, and then it would be 3. So this basically just lets our sequence build. And once this while loop is done, we want to make sure that we are updating the length of max length if the local length we've computed is longer than max length. And what we're going to do is use JavaScript's built-in math.max function, which just compares any number of numbers and will return the greatest number. So what we're going to do is we're going to compare the current value of max length to the new computed value of local length. And that'll give us the max number, and this algorithm this for loop will run, and at the end of it, we will have the length of our longest consecutive sequence, and that's the whole algorithm. Okay, so let's just go ahead and submit this solution on Leetcode. Gonna copy that there, and we'll hit submit, and you can see that it was a success. Not running at the most optimal time, but on an interview, this is the optimal solution. Maybe you find ways to save a little bit of computation time somewhere, but it's not going to change the big O evaluations of either space or time.